Welcome to Archicraft, a bit of architect, your go-to podcast for modern software and solution architecture, enterprise strategies, and AI-powered engineering. Each episode is AI narrated, based on the original blog content by Dima Golodiuk at demongo.com.
You're listening to the episode number 3 of the podcast. This episode is titled Agentic AI, Distributed Systems Challenges. In this episode, we explore a senior architect's take on agentic AI. The real challenge isn't the large language model, but the distributed systems architecture needed for reliability and scale. We'll dive into why concepts like state management, fault tolerance, and concurrency are the true hurdles to building production-grade agentic systems, and how to tackle them. Let's get started.
Welcome to the deep dive. Okay, let's unpack this agentic AI thing. It's everywhere, right? You hear all this buzz about large language models, how they can reason, plan, use tools. It's amazing stuff. But if you're like us, maybe you're starting to wonder, what's the actual engineering challenge here? Especially when you think about, making this stuff work reliably in the real world. So today we're digging into a really sharp perspective from Dmytro Golodiuk, who's a senior architect, and he put out this piece called Agentic AI, Distributed Systems Challenges. And his main point, it's pretty stark. He says the real hurdle, the big problem, isn't the AI model itself. It's the complex distributed systems architecture you need underneath it all, to make these agents reliable, scalable, enterprise grade. So this deep dive is definitely for you if you're maybe a CTO thinking about production, or a CIO planning strategy, or an architect actually mapping this stuff out.
Yeah, it's quite striking how blunt Dima is. He basically says the industry's obsession right now with just the LLM capabilities, bigger models, better prompts, is a profound misdirection. It's like focusing only on building a super powerful engine, but completely forgetting you need a chassis, brakes, a steering wheel, the whole system around it. He argues that moving from like a cool demo on your laptop with one agent to potentially hundreds or thousands of autonomous agents doing complex, long-running jobs inside a company, well, that forces you right back to classic distributed systems problems. Things like state consistency, fault tolerance, how agents coordinate, governance, all that hard stuff we deal with over unreliable networks. And there's this other layer too, which is fascinating. What happens when an agent messes up? It might not just be a technical bug, like a null pointer. What if it's what Dima calls a failure of cognition? The agent hallucinates something, or it just makes a bad decision based on flawed reasoning. That kind of non-determinism, it completely changes how you have to think about building resilient systems, doesn't it?
It's really a wake-up call for architects. We need to bring those hard-won, battle-tested, distributed systems principles into this whole new AI world.
That difference between a technical bug and a cognitive failure, that really hits home. It shows why you can't just plug an LLM into your existing setup and expect magic. So, okay, how do we start building then? Dima doesn't suggest jumping straight to like a massive swarm of agents. He lays out this kind of evolutionary path. You start simple and add complexity, but each step brings new trade-offs, new challenges, scars, as he calls them. The first step, the entry point, is what he calls a deterministic chain. Think basic array retrieval augmented generation. It's a fixed sequence. Retrieve some info, add it to the prompt, generate the text. That's it. No dynamic choices being made by the AI. It's predictable, sure, and relatively easy to debug because it always does the same thing. Great for really well-defined tasks, but it's brittle, super brittle. The moment something unexpected happens, something outside its fixed path, it just breaks, doesn't know what to do. Okay, so from that chain, we level up to a single agent with tool use. And honestly, this seems like the sweet spot for a lot of initial enterprise projects. Here, you have one agent powered by an LLM, and it uses its reasoning ability to figure out which tools it needs to call and in what order to get a job done. And these tools aren't just reading data, they're actions. Calling APIs to update a system, sending an email, querying a database, whatever. It gives you a lot more flexibility, but it's still kind of contained. You can observe what this one agent is doing. The downside, though, is that it's still a bottleneck. Dima calls it a monolith in terms of reasoning. One agent doing all the thinking limits how much complex work you can do in parallel.
Right, a reasoning monolith. That's a good term for it. And that bottleneck is exactly where the real distributed systems pain starts, like Dima points out. When the task gets too big or needs different kinds of expertise, That's when you have to break it down. You move to a multi-agent system. You create a team of specialized agents, and now you have to make some really fundamental architectural choices about how they work together. DEMA lays out three main patterns for this multi-agent collaboration. First up is the Orchestrator-Worker pattern. Classic stuff, really. You have a central boss agent, the orchestrator. It takes a big goal, breaks it into smaller tasks, and hands them out to specialized worker agents. These workers can often run in parallel. You see this in some research systems, like Anthropic's setup, where a lead researcher agent manages others, the big plus. Centralized control, you can see what's happening. But the huge minus, that orchestrator is a single point of failure. If it goes down, everything stops. And it can become a massive performance bottleneck if it gets overloaded trying to manage all the workers. Okay, second pattern. Decentralized choreography. People often call this the group chat model. Here, there's no central boss. Agents just kind of react to things happening in a shared environment. Maybe they publish messages, others read them and react. It's emergent. The big advantage here is scalability and resilience, right? No single bottleneck or point of failure. Sounds good. But, and this is a big but, DEMA calls it an absolute nightmare to debug, govern, and comprehend. Imagine trying to follow one business process through that mess of messages, and you lose explicit control, which is pretty scary if you're in finance or healthcare or any regulated field. Oh, and the hierarchical pattern. It's basically just stacking orchestrator-worker patterns recursively, which just makes the coordination even more complex.
Yeah, that nightmare to debug part is definitely a warning sign for any architect. Okay, so building on that, whichever collaboration pattern you choose, there's this other critical decision. How do these agents actually talk to each other? DEMA is really strong on this. He says direct synchronous calls, like Agent A making a direct API request to Agent B and waiting, that's a path to ruin. Why? Because it creates tight coupling. If Agent B is slow or down, Agent A gets stuck waiting. Problems just cascade through the whole system. It's fragile. So the much better way, he argues, is to use an event-driven backbone. This changes everything. Instead of Agent A calling B directly, Agent A just publishes an event like, hey, task created or data ready onto a shared durable log. Think Apache Kafka, for example. Then Agent B, or maybe a whole group of Agent Bs, subscribes to that event stream. When they see an event they care about, they pick it up and process it asynchronously. When they're ready, it completely decouples them. And the benefits are huge, right? Operationally. You get scalability. In your processing power, just add more worker agents to the group. Kafka handles distributing the load. You get resilience. If one worker agent crashes, Kafka automatically gives its work to another healthy one. And fault tolerance. That event log is immutable. It's your source of truth. If something goes wrong, you can replay events, rebuild state. DEMA basically says this is the difference between a fragile demo and a real production system that can handle chaos.
Exactly. And that idea of the immutable log as the source of truth leads us right into the next big challenge, state. Agent memory. I mean, an agent without memory is useless, right? You can't remember what it just did, can't learn, can't manage a task. That takes more than one step. But we're not just talking about the LLM's short-term contents window here. We're talking about persistent state, like the business process state. What step are we on in this insurance claim? Has the payment been made? What happens if the server on your agent just reboots halfway through processing a huge multi-million-dollar purchase order? You can't just lose that state. This throws us straight back to Brewer's CAP theorem. Remember CAP, consistency, availability, partition tolerance, a cornerstone of distributed systems. And the reality is network partitions, bits of your system being unable to talk to each other, they will happen. That's a given. So partition tolerance isn't really a choice. The real choice you, as the architect, have to make is between consistency C and availability A. And this choice has massive implications for how your agents function. So if you build a CP agent system, prioritizing consistency over availability, then correctness is everything. If an agent can't be 100% sure it has the absolute latest correct piece of data, maybe can't reach the main database, it just stops. It refuses to act. It becomes unavailable. This is essential for things where being wrong is disastrous. Financial transactions, critical medical decisions, compliance checks. You need correctness, even if it means the system halts sometimes. On the flip side, you have an AP agent system availability over consistency. Here, the main goal is to always respond, always be available. If the agent can't reach the primary source of truth, it might use slightly older cached data. It keeps working. This is totally fine, even preferable for things like product recommendations or maybe summarizing news articles. Getting a slightly stale recommendation is way better than getting an error message. The system is more resilient, but you trade off guaranteed consistency.
Okay, so this AKP theorem thing, it means agent memory isn't just one big chunk of data, right? DEMA makes this really important point. Agent state is actually a composite. It's made up of different kinds of state, and they likely have different consistency needs. Think about it. An agent probably has short-term memory, like what we're talking about right now, the current task context, often held memory. Then there's long-term memory. It's knowledge base, maybe stuff in a vector database it uses for RG. And then, crucially, there's transactional state. This is the record of where we are in a long-running business process, like step 3. Payment processed, waiting for shipping confirmation. This needs to be durable. And these different types demand different soul type piece choices. That transactional state for an insurance claim, that has to be strongly consistent. CP, no question. But the long-term knowledge base, maybe that can be eventually consistent. AP is probably fine. It's okay if it takes a few seconds for the absolute latest company memo to appear in its knowledge. So architects need to design for this hybrid state model. The agent's logic itself has to be smart enough to know which data source is the gospel truth, CP, and which might be slightly out of date, AP. That's a level of sophistication, Dima says, is often just overlooked.
Completely overlooked. And that complexity leads right into the next minefield, failure. Because things will go wrong. It's not an if, it's a when. Especially when you have multiple agents, complex processes stretching over time, like processing an insurance claim or managing a whole supply chain move. An API might be down, a network link might drop, or going back to that cognitive failure idea, the agent might just make a bad call based on faulty reasoning. In these long processes, you can't just lock up all the resources for hours hoping it eventually works, and just retrying blindly. That's often naive or even dangerous. We need a way to cleanly undo things that have already been done. And this is where the saga pattern becomes absolutely critical. It's the standard solution for managing consistency across distributed services without using fragile blocking transactions like two-phase commit. Basically, a saga breaks down a big transaction into a sequence of smaller local transactions handled by different services or agents. Each step, if successful, triggers the next one. But here's the key. For every step that makes a change, there must be a corresponding compensating action that can undo that change. If any step fails, the saga runs the compensating actions for all the preceding successful steps in reverse order to clean things up.
Right, compensation is key. And like the collaboration patterns, sagas come in two main flavors too, don't they? There's the orchestration-based saga. Here, you have a central orchestrator, kind of like the Orchestrator-Worker pattern we discussed. It knows the whole workflow, it sends commands to each agent, do step 1, waits for a reply, then sends the command for step 2, and so on. If something fails, the orchestrator is responsible for explicitly calling the compensating actions. Undo step 1. It's easier to follow the logic because it's all in one place. But again, that orchestrator is a single point of failure and a potential bottleneck. Then you have the choreography-based saga. No central controller here. It's event-driven. Agent 1 does its work, publishes an event like step 1 complete. Agent 2 sees that event, does its work, publishes step 2 complete. Compensation also happens via events. Maybe an order-failed event triggers compensating handlers in previous services. This is much more loosely coupled, scalable, resilient, all the good stuff from event-driven architecture. But, Dima points out, trying to figure out the overall status of a business process can get really tricky because the logic is scattered everywhere.
Exactly. And this is where Agentic AI throws a massive curveball into the traditional saga pattern. It's really interesting and honestly quite challenging. In classic sagas, compensation is usually pretty straightforward and technical. If the action was charge credit card, the compensation is refund credit card. Simple reversal. But what's the compensation for an agentic action? An action that involves complex reasoning, maybe even creativity. Dima gives some great examples. Let's say an agent's job was draft a personalized apology email to this customer about their delayed shipment. Okay, it drafts and sends it. Now let's say a later step fails. You can't just unsend or undraft that email, can you? Or imagine an agent responsible for logistics. It analyzes a weather forecast and decides to reroute our entire shipping fleet to avoid the storm. Later, it turns out the forecast was wrong. The compensation isn't a simple database rollback. The compensation is another complex reasoned task. Okay, agent, calculate a new optimal route based on the updated information and communicate those changes effectively to all drivers. So with agents, compensation itself becomes a semantic, goal-oriented task. It might require another agent, or the same agent, to reason and act again. Fault tolerance gets deeply tangled up with the agent's core reasoning abilities. You have to plan for this from day one.
Wow, okay. That's a huge paradigm shift for error handling. It's not just technical rollback, it's semantic recovery. That's complex. All right, moving towards the end here, another massive challenge, especially as we scale up. Concurrency. You've got potentially hundreds, thousands of these agents running around doing things in parallel. How do you stop them from, stepping on each other's toes? Corrupting shared data, deadlocking. The traditional ways we handle concurrency, things like shared memory, locks, mutexes, they really don't fit well with these distributed autonomous agents. They lead to bottlenecks and complexity. This is where Dima brings up the actor model. He argues it's an exceptionally good fit, almost purpose-built for this kind of system. The core ideas just map so well. Everything is an actor. Think of an agent as an actor. It bundles its own private state and its behavior together. Crucially, an actor state is encapsulated. Nobody else can directly touch it. This eliminates whole classes of concurrency bugs like data races. Actors only interact by sending asynchronous messages to each other's mailboxes. They don't block waiting for replies. When an actor receives a message, it can update its own private state, send messages to other actors, or even create new actors. Frameworks like Akka, or languages like Erlang and Elixir, or platforms like Microsoft Orleans with its virtual actors, they're built on these principles for massive scale and resilience.
Right. And that naturally brings up the question. Okay, we talked about event-driven architecture with Kafka earlier, and now the actor model. How do they relate? Are they alternatives? Do they compete? Dima makes a key clarification here. They are absolutely complementary layers. They work together. They don't replace each other. It's not an either choice. Think of the actor model as the microarchitecture. It's about how you structure the internals of a single service, or maybe a closely related group of agents running together. It's focused on managing concurrency safely and efficiently within that boundary. How does this specific agent handle multiple incoming requests without corrupting its state? How does it talk to its immediate neighbors efficiently? That's the actor model's job. Event-driven architecture using something like Kafka is the macro architecture. That's the robust, persistent communication backbone between different services, different swarms of agents, different bounded contexts across the whole enterprise. It answers the question, how do we make sure the claims processing group can reliably send a message to the fraud detection group, even if the fraud system is down for maintenance for 3 hours and comes back later? That persistence and decoupling is key. So the most robust systems will likely use both. The actor model for managing the high-speed concurrent interactions inside agent services, and the event bus for reliable asynchronous large-scale communication between those services.
That distinction is super helpful. Microarchitecture versus macroarchitecture. Okay, finally. Let's say we do all this. We build the most elegant, resilient, scalable, agentic system. There's still one huge piece missing, especially for any real business. Governance. If you can't govern these things, if you can't control them, audit them, secure them, it's just an unacceptable risk. Plain and simple. This is the stuff keeping CTOs and chief risk officers up at night. It's absolutely non-negotiable. Dima flags several critical governance challenges. First, basic security and access control. How do you enforce least privilege? How do you stop, say, a marketing agent from somehow accessing sensitive HR records or calling a financial API it shouldn't touch? An agent with too many permissions is a massive security hole waiting to happen. Then, cost control. LLMs cost money every time they think. What stops a buggy agent getting stuck in a loop and racking up a 6 or 7 figure cloud bill before anyone notices? You need circuit breakers, budgets, hard limits, auditability, and explainability. This is huge. If an agent makes a really important decision, denies an insurance claim, approves a big loan, you have to be able to understand why. And that's incredibly hard with models that are often seen as black boxes, especially non-deterministic ones. And finally, data privacy. As agents interact and pass data around, how do you prevent them from accidentally leaking sensitive customer data, PII, or confidential company info across different systems or contexts?
Yeah, these are the showstoppers for enterprise adoption. And Dima points towards a research paper on something called Saga, a security architecture for governing agentic systems, as a blueprint for what's needed. Even though it's research, the core ideas are spot on for what a real enterprise governance framework needs. It talks about needing a centralized provider. Think of it as a trusted authority, like an identity service for agents. It registers all legitimate agents, knows who they are, prevents random shadow agents popping up. Then you need user-defined policies. The business needs to define the rules. Which agents can talk to which other agents? What tools or APIs is Agent X allowed to use? These policies are enforced by the system. And finally, it uses cryptographic access tokens. When agents communicate, they use short-lived, secure tokens issued by that central provider to prove who they are and what they're allowed to do. This limits the damage if a token is compromised. Diva's warning here is really stark. He says basically most proofs of concept he sees just ignore all this governance stuff. And that, he says, is a critical mistake. Because the very autonomy that makes these agents so powerful also makes them potentially dangerous. A vulnerability in one agent or one compromised agent could spread damage rapidly across every system it touches. So the big takeaway is, governance can't be bolted on later. It's not an afterthought. You have to design and build the architecture for security, for auditability, for control from the beginning. That provider system, that's your foundational control plane. You need it before you let agents loose anywhere in your production data. Without it, Dima says you're building something ungovernable, untrustworthy, and ultimately just too risky for any serious enterprise.
Right, and that really brings us full circle. Dima's core message is crystal clear. Getting agentic AI into production successfully isn't going to happen just because we get slightly bigger LLMs or write slightly cleverer prompts. It's going to happen because we apply disciplined, rigorous, well-understood principles of distributed systems architecture. That's the real work. We've covered those key pillars today, haven't we? Choosing the right collaboration patterns, chains, orchestrators, choreography, understanding the trade-offs, recognizing that agent state isn't simple, needing that hybrid CIP model, adapting the saga pattern for this new world of semantic compensation when agents fail, using the actor model as that microarchitecture for concurrency, working with an event-driven macro architecture, and maybe most crucially, building in governance not as a feature, but as the absolute foundation right from day one.
Absolutely. And Dima's final thought for architects, I think, is really profound. He says, look, the large language model is just the reasoning engine. Yes, it's revolutionary technology, but it's still just one component. It's one piece inside a much larger, much more complex, and frankly, much more challenging machine that we, as architects and engineers, are now being asked to build and operate reliably. So the real question this leaves for you, our listener, is this. How are you going to shift your focus? How do you move beyond just the prompts and the models and start thinking deeply about the fundamental distributed systems engineering that will actually make agentic AI work safely and effectively in your company? What does starting with the architecture, not just the prompt, really look like for your next big AI project? Something to think about.
Thanks for tuning in to Archicraft. This episode was generated using AI from Dmitro Golodiuk's blog at demongo.com/news. If you enjoyed this episode, follow the show on your favorite platform and share it with fellow architects and engineers. Until next time, build smart, architect with intent.